as we stated earlier, enthalpy is a state function. It doesn't matter the path that we take to get to a certain situation. And so it turns out that we can write thermochemical equations which relate a chemical reaction to the amount of heat that is involved. For example, we have here the reaction of elemental hydrogen with elemental oxygen, producing 1 mole of water in the gas phase. And so in this case, since we have a fractional amount of elemental oxygen and we're only producing 1 mole of the product water, the enthalpy that is produced, in this case negative 286 kilojoules, is the enthalpy per mole of the water that is produced. And this is a useful quantity to keep track of because we refer to this as the heat of formation of 1 mole of this particular compound being water. Likewise, if we did the reaction where we did the combustion of methane, this particular reaction would produce carbon dioxide and 2 moles of water. In this case, the delta H is also negative because it's an exothermic reaction. And of course, in this case, it produces 882 kilojoules of energy for every 1 mole of carbon dioxide and 2 moles of water. If we were to double that, of course, then we would produce twice as much heat. So, in both of these reactions, the reactions are exothermic, and hence the delta H's are negative. Our final example is a reaction that is between acetylene and oxygen, producing 1 mole of water and 2 moles of carbon dioxide. This produces 1,238 kilojoules of heat, and you'll notice that the sign of delta H is also negative, so it's an exothermic reaction. So we can emphasize this a little bit further in reminding you that enthalpy is an extensive property. It depends upon the amount. So if we look at a reaction where we do the complete combustion of methane, if we produce only 1 mole of CO2 from the 1 mole of methane, this would produce 802 kilojoules of heat. Notice that delta H is negative. But if we did this reaction and doubled the number of moles of methane that we do the reaction with, this produces then twice as much heat as a result of doing this reaction. Likewise, if we were to change the direction of this reaction by flipping a reaction around, what this simply does then is changes the sign of the enthalpy, indicating then that the reaction would be endothermic rather than exothermic. So in this case, we had the reaction of methane and producing carbon dioxide and water. The delta H is negative, that's exothermic, but change the direction of the reaction by switching the reactants and products, and that would require then that the delta H would become positive. The heat would also be a reactant. Finally, the enthalpy of a reaction depends upon the phases associated with the reactants and products, because phase changes involve either adding or removing heat, and so that can affect the amount of heat involved in the reaction. So in this example here, we've done our complete combustion of methane, producing gaseous CO2 and water. However, if we were to do the reaction such that it produced gaseous CO2 but liquid water, you'll notice that then the liquid water would then produce slightly more heat because going from the gas phase down to liquid phase requires that we remove heat from the system, in this case the water, and to get it to become the liquid. So as an example of a question that you might be asked, in this case, if we took 1 mole of calcium oxide and reacted with water to produce solid calcium hydroxide, this is sometimes referred to as lime, it releases 65.2 kilojoules of heat. So if we first ask, is this an exothermic or an endothermic reaction? The key term here is releasing the heat, and so as a result, the reaction must be exothermic. If our second question is what is the value of delta H for this particular reaction, well, the value of delta H has to be negative 65.2 kilojoules, the amount of heat that was being produced. And of course, delta H is always negative if the reaction is exothermic. Finally, we write the balanced thermochemical equation. In this case, we have to first write the formula for calcium oxide, and CaO will react with our water. Those are our two reactants. And then our product is going to be calcium hydroxide, calcium being 2 plus and hydroxide being 1 minus. That requires there be 2 hydroxides in the formula of our product. Now we have to make sure that the reaction is balanced, and so we see that we have 2 oxygens on the left-hand side. There are also 2 oxygens on the right-hand side, and likewise there's 2 hydrogens on the left and 2 hydrogens on the right, so it is balanced. And the delta H is included as being the negative 65.2 kilojoules per mole. All right, in this particular case then, what does the enthalpy reaction be if the amount of calcium oxide and water were doubled? Well, if we double the coefficients, then we're also going to have to double the heat, and so as a result we would produce 130.4 kilojoules, or twice as much as we had heat that we produced when there was only 1 mole of calcium hydroxide produced. As an example of how to use the heat of a particular reaction in a calculation, we have a question that says, how much heat is required to melt 56.8 grams of a block of ice? In this case, the reaction involved is a physical reaction where solid water or ice is converted into an equivalent amount of liquid water. The heat of fusion of ice is positive 6.01 kilojoules for every 1 mole of water. And so the process in this case would require that that amount of heat would be put into 1 mole of ice to produce the liquid water. So the calculation will involve the melting process, and we know that in this case the heat would be equal to the number of moles, the N in this equation, times the heat of fusion, which would have units of kilojoules per mole. So if we plug our numbers into the calculation, first of all we have to convert the 56.8 grams of water into moles. So we use the molar mass of the water, and then that cancels the grams, and then we use our heat of fusion, and we write this so that the moles of the water will cancel, and in this particular case then we end up with 18.94 kilojoules, but there's only 3 significant digits, so the tenths place is not rounded up, and so our final answer is 18.9 kilojoules. As another example, the reaction of tetraphosphorus decoxide with water produces phosphoric acid and evolves, in this case gives off 452.8 kilojoules of heat as given in the reaction below. So in this case the delta H is negative, so heat is being produced by this reaction. And so in this particular case, it asks how much heat is evolved when 26.4 grams of the P4O10 is reacted with an excess of water. So again, we're going to calculate our heat, and we're going to start with the mass of the P4O10. We need to convert that into moles. And so we need the molar mass of P4O10. This is calculated by summing together all the atomic masses of 4 phosphoruses and 10 oxygens. We write this so that the grams will be canceling, and at this stage we have moles of P4O10. And at this point, if we multiply by the 452.8 kilojoules per mole, and this would then give us the canceling of the moles. At this stage, then we can do our math, and we see that we end up with a negative 42.10 kilojoules. Should be only 3 significant digits, and so 42.1 kJs. So, how much heat is evolved when 26.4 grams of H3PO4 is formed? It would be a similar question. In this particular case, then, we're going to calculate our heat by, first of all, converting the grams of the phosphoric acid into moles using its molar mass. And so in this case, then, we multiply that by the amount of heat that is being produced. In this case, there are 4 moles of H3PO4 for the negative 452.8 kilojoules. The moles of phosphoric acid are going to cancel. And so in this particular case, then, we do the math, and we are going to end up with 30.49, in which then rounds to 30.5. As a further example, we can look at the complete combustion of methane gas, often used to heat homes. And so for the reaction that is given here, we have a heat of this particular reaction, which is going to produce 802 kilojoules. In this particular case, then, notice that it's negative, so this is heat that is being produced or is a product of the reaction. The question asks how many grams of methane are required to provide the 980 kilojoules of heat, and so in this case we would start with that as the given. So we're trying to figure out the mass of the methane, and so we start with the 980 kilojoules. We use our heat of the reaction to convert between the kilojoules, the amount of heat, and the moles of the methane. So for every 1 mole of methane, it produces 802 kilojoules. And so the kilojoules will cancel. We then can use our molar mass of the methane to go from moles to grams, canceling the moles. And at this stage, if we did the math, we could end up with the number of grams of methane required to answer this question. So put that in your calculator, you get 19.60, rounding to the appropriate 3 significant digits.